So I think we should probably start. We're recording now.
Okay, cool. All right, so let's see. Let's start this again. Okay. So for both knowing about how things are going and to just see if the raising hand feature works, can I see a show of hands out of the three of you who's actually read milestone 4? All right, awesome. Cool. Okay. And yeah, it can be quite a bit, so but it's also a lot of fun. So we're gonna quickly introduce it and talk about how to further optimize it through parallel methods. Okay, let's see here. Oh,
sorry. Trying to get this off the screen.
okay, cool. All right, so yeah, just I guess a precursor here. This is the first time I've ever done an online lecture here, so I'm learning along with the rest of you. So we'll see how it goes. Okay, so for milestone 4, you're going to be building on top of all the other milestones that you've done here, and this one specifically is the traveling courier problem here. So this is a popular problem in computer science. So have, again, maybe a show of hands, who here has heard of the traveling salesman? Okay, well, that's also fine. We're gonna roughly go over it, right? So you have a few problem constraints here. You have depots. So depots are where you have all your goods, or sorry, depots are where you want to deliver your goods. You have pickups. You have,
So maybe we just jump in. So that we've gone over this in lecture. So depots are where
yeah,
they get the truck from to start, and then
yeah,
you got pickups and drop-offs, and you got a constraint on truck capacity. So they've got traveling salesmen with some extra constraints.
yeah. Given these constraints, you want to find the fastest delivery route, and a question is how. So let's see. So you want one method is to estimate the time between all locations. And given that, you want to find a good delivery ordering. So this is a very computationally difficult problem. And then finally, you want to return that to the user. So once you know the travel time between all locations, you've ordered that over, you can give that final one back to the user. And you have 45 seconds. So what this means is you could find multiple orderings that make sense. And in the 45 seconds, we will take the best one. So one common methodology could be is to just get a crude basic ordering first and massage it in the next 45 seconds. And at the end of the 45 seconds, we'll see the best one that you can give to the user. So you can imagine that this is a matrix of problems here. So on one side, we have the representation of the starting intersections, and on the other side, we have the destination intersections. So one option is we can estimate by distance. So this is, it's fast. You can think of maybe like a Euclidean distance problem, but it's inaccurate because it doesn't take into consideration the path, right? Two things, for example, might be really close by, but if there's no road to get there, then it's actually a lot more costly of a route than it looks like. A more accurate representation is the exact path, but as you could guess, that's quite slow to do for all your potential paths in your problem. Okay, so roughly here is the algorithm here. So we have, you can see here, it's a nested loop. So at the outer loop, we have our source intersections, and inside we have our destination intersections. You can other parameters that we have k depot or pickup drop off intersections, and in total we have n total intersections here. So out of the three of the students here, maybe a poll would we would want to see a poll here of what you think the complexity of this is. So just roughly, you things to consider before answering is maybe have a look at the nested for loop structure that we have. Try to remember what the pathfinding algorithm for one such iteration is, and look at the constraints. So we have k depot pickup drop-off constraints and n total intersections. So given this information, maybe I could get some participation to see what you guys think the complexity of this is.
So let me quickly jump in. So can everybody see, just type into the chat or raise your hand or something. Can you see the poll? Somebody type, I can see it or I can't see it. So.
So I cannot see it.
All right. So I've launched the polling. Let's see. You cannot see it. Why not? That's strange. Okay, because the poll has been launched. All right, let me see what I'm doing, what's going on here. I haven't done one of these two-headed presentations before. Let me quickly see if that changes anything. Can you see it now? Okay, I'm going to do a new share. I'm going to share this. Okay, now can you see that poll?
I still can't see it here.
Let me end the polling. Let me try again. Relaunch polling. Okay.
Oh, yep. I see it, and so
There must have been something strange with the fact that you were controlling it and I was launching it. So can people see it now? Okay. So yeah, as Nath said, this is basically what we talked about in lecture. We're trying to find the exact travel time. So we're using our pathfinding algorithm to find them. And the most straightforward way to do it is to use our A-star algorithm. And we've done a double nested loop here. So we're saying from every start intersection, so all the interesting K intersections to all the interesting K intersections, so a double nested loop, we're going to call A-star every time. A-star is a good algorithm for going from one source to one destination. What is the complexity of this? And you'll see in your final presentation, there's a Q&A. TAs love questions like this. So these are good ones to practice on. You know, what is the complexity of this algorithm? What do you think of this algorithm versus that algorithm? So jump in with your poll. I can see people are answering. Got a few more people. Take a shot at it. If you're on the line and they haven't taken a shot at it, go for it. Actually, it looks like, okay, it looks like we got it. So I'm going to end the polling. And by a landslide, it was k squared n log n, which is exactly right. Okay, so A-star is n log n, so searches the whole graph or close to the whole graph. So that's n, uses a priority queue. So that's sorts all those things in a log n computation, all the nodes. And then we've got a doubly nested loop. K interesting intersections, so that's k squared. So yes, well done. Let me share the results. Click on this button here, and you'll be able to see that you all, whoops, I think I'm fighting the mouse with Nath here.
oh, sorry. Yeah.
Okay, so there you go. You should see that now. And with that, I'm going to close this poll. Everybody see that? Okay, I think we're good. Nath, why don't you keep on going?
Okay, cool. Is the presentation running on a second monitor, Vaughn?
That looks like it did do a weird thing. Okay, let me swap the presenter view and the regular view. Let's see, how do I do that? How would I do that?
Okay.
I think maybe stop the presentation. Let me start it again. Because I think I need to swap the presenter and slideshow view. All right, let me do a different share then. You know what? We'll do a new share and I'll just share the other screen. Can you see it now?
No.
All right. Let me stop the sharing. Let me reshare. Okay. Somehow gotten into a strange state now. I have not actually seen that happen before. I need to swap the presenter view with the All right, let me try to sharing the other one. This is stop that sharing and
My phone froze there.
I think we've gotten into a strange state here. All right, I think I got rid of it there. Let's see what happens now. Okay. Okay, I'm just like gonna reopen the PowerPoint presentation because that got pretty confusing. It keeps bringing it up in the other order. Let's see. Are you still in the Zoom meeting, Nafe, or what?
Yep, I'm here. Should I try sharing?
Yeah, why don't you try it? I'm not sure what's going on. I don't even see the meeting controls now. So
Okay, I'll do that right now. Let's see here. Okay, okay, let's see here.
I mean, I can see that. This is not in slideshow mode.
Okay. Can people, oh, I'm having the same problem here. Let's see.
Click on, yeah, I'm not sure. We could go through it, I guess, not in presentation mode if necessary. Okay, that looks pretty good.
Okay. All right. Yeah, we're all learning here. This is interesting learning experience. Okay, yep. It looks like overwhelmingly most of you have gotten the complexity, which is good. Again, we can see from the nested loop structure, and we know the roughly the algorithm for the A star approach between a source and destination. So you can imagine that this can be quite big, especially if we get a lot of depot and pickups because of the k squared in this in the big O notation. So we might want to look at potentially another approach here. So if we look at Dijkstra, we can actually the multi-target Dijkstra, if you see this, is that we don't need the second loop here. Because of the single loop iteration, we can think that this algorithm might be different here. So given the single loop, can we get, okay, so we have 1. Can we see more people participating in this poll? All right.
Okay, so we have a few more seconds for the last person. Okay, we're gonna close this and share the results. And yeah, you guys got it exactly right.
Yeah.
It's kn log n. So we've gotten rid of a factor of k, which can be a lot for a big problem. Okay, I'll stop sharing that. And Nate, take it away so I don't mess up your presentation.
Yeah. So yeah, and this is exactly because we got rid of one of the nested loops here, right? So one of the loops that was iterating k times, we've gotten rid of it. And because of that, we can actually get it in k of n log n. So now the question is, okay, this is really good serial speed here, or as good as we can do, right? But what if we wanted more speed? Well, the approach for that could be parallel programming here. So
Nate, we went over some of this in lecture, so we can probably blast through this pretty fast. Okay.
Okay, cool. All right. Roughly, we have multiple CPU processors, and they can communicate with one another through shared memory here. So each core can execute its own instructions. They have common shared memory. And if you wanted to learn more, you can take computer architecture. There's also operating systems next year, which is 345, that teaches you how the operating system actually schedules threads onto multiple cores. And yeah, there's a lot we can do there. So applications with a single thread, most of the applications that you've been taught use a single thread here. So it's running on one of the cores that has access to all of the shared memory. Single threaded cores, you don't have to worry about the implications of sharing memory. So you can imagine if multiple cores are sharing the same memory location, there can be complications, which we will demo later today. So here is a multi-threaded application here. Multi-threaded applications do need to worry about sharing memory. There can be inconsistencies. If, for example, if one core is modifying a variable that another core is reading here, there can be inconsistencies in what they expect the value to be. So for that, we have to consider how to share memory. Now, here is an example of simple parallelization, and we're gonna actually upload some simple code that does something similar to what you see on the screen, so you can actually implement a parallel pragmas into your own code here. So here is a vector addition, and the nice thing about this is that all iterations of this loop are independent of each other. So A of I, B of I, and C of I, each iteration of I doesn't depend on another iteration. So hence, this is what we call an embarrassingly parallel problem. Here, we see that in our machine here, we have a 4-core machine. Hence, we can spawn 4 threads, and each thread is forked off to get a quarter of the problem size. So our whole problem size is 100 different iterations of the loop. We give each thread 25 different iterations. And then afterwards, after the loop is done, so the parallelization is around the for loop. After the loop is done, we serialize again to a single thread, which that thread prints out done. And here I'm going to share a very simple program that actually does that. So, and we'll also upload this program to all of you so you can take it and implement it in your own code. So I'm going to end it.
Already, so you guys can see it right now.
So I'm going to end.
It's been uploaded.
Yeah, I'm going to end this screen share, and I'm going to share the demo right now. Okay, so give me 1 second here. Okay, so so this is the code that was given to all of you as well, but roughly we're gonna try a few things, okay? So, okay, so this code is very similar to what what we even have in the slides here, but we've complicated it a bit. So in the slides, we had a very simple vector addition. Here, we've added a bit more computation. And the reason being is we wanted to have more work for the processor to do. So one thing that we'll see is that there is overhead for parallelization. There is overhead for OpenMP. And in order to amortize some of this overhead, we want to have more compute. So for example, with 4 threads, you might think that we should be able to easily get 4 times the amount of performance, but that's not always the case because there is an overhead that we have to pay. We can amortize more of that overhead by having more compute. So that's why we've added a bit more compute to show that we can do some of that. So instead of a vector add, we have a few multiplications and a modulo operator. The other thing that we can modify here is we have the size of our problem size that we modify. So here is this vector length pragma, which I'm going to try to modify it to 4 different values to show you how the sizes affect the speed up that we expect. So what I'm going to do right now is I'm going to compile this, and what we're going to do is we're going to have a problem size of 1,000, and we're going to have parallelization on. Okay, and let's give this a shot and let's see what happens. Okay. And all right, so we've seen an elapsed time of about 0.0012. Okay, so this is parallelized implementation of a problem size of 1,000. So we might expect it should get faster if I throw more threads at the problem here. So let's see here. I'm going to enable, or sorry, I'm going to disable parallelization, and I should expect it to get slower. So we've seen that in the parallel form, it was 0.0012 of elapsed time, and I expect it to get slower with serialization. So let's see what happens here. And that's not what we see here. We actually see that it got quite a bit faster with the serial threaded approach. And that is because we didn't give our parallel problem enough work to do. We were paying an overhead for parallelization, but we haven't amortized that overhead with enough work. So that's what I'm going to do right now is I'm going to increase the amount of work that we do. I'm going to increase the amount of work that we do, and I'm going to leave it serial. So right now it's serial with quite a bit more work. And let's see what happens here. Okay, so the serial threaded approach we see at about 0.003, and let's try to multi-thread this. So to multi-thread, I'm going to uncomment my pragma OpenMP. And we see a bit of a speed up here, right? So before it was 0.0033, and now we see at about 0.0022. So this is a bit of a speed up, but maybe we can actually throw more work at it. And let's see if we see more of a speed up here. So right now I'm gonna throw more work at it, and it's parallel. And I see it's at about 0.09 or 2.1, okay? And I'm going to serialize it, and we can observe the speed up. So to serialize it, I'm going to and that's exactly what we see here. So we see serially it's running at 0.33, whereas in the parallel implementation, we saw at about 0.1 or a little less than 0.1, depending on the run. So overall, it's a little less than 4x speed up that we see once we've increased the work to a sizable amount. And that again is because there's always a bit of overhead that we have to pay, right? So we have 4 threads, but there is a bit of overhead. Here, this is almost as good as it can get. You might realize that right now we have quite a bit of computation even in our loop. But if we weren't bounded by computation, but we were bounded by memory, we might not even see this kind of speed up as we increase the amount of cores that we throw at the problem here. So it really depends on the computation or the nature of the computation that you have.
Nate, can you do one more quick thing? You can show how to print out the number of threads, but show that it does
yes,
quite a bit.
sure. So,
and I guess maybe one comment I'll put in about overhead. Creating a thread actually takes a reasonable amount of compute. So that's the key reason that the small versions are not getting speed ups, is the action of creating threads takes a reasonable amount of time. So if there's not much work to do, it's not worthwhile.
So now I've uncommented. I'll show that line again, but we're gonna see that we can actually print the number of cores that we have, or the number of threads that we have in our compute. So here we have 4 threads because we're running on a 4-core machine with no hyperthreading. So if we actually look at how to print that, it's this line over here. OpenMP get num threads, and this actually takes some time. So which is why for the most part, when we want to actually measure the performance of our application, we comment it out. But for the sake of actually seeing the number of threads, we can put that back in and print it. Okay, so I'm gonna go back to the slideshow unless if anyone has questions, and you can ask that in the chat or unmute yourself. There's not too many people here, so it's totally okay to just unmute and speak if that's okay. All right. Okay, I'm gonna stop this share and I'm gonna go back to the presentation. And Vaughn, I've also given you remote control of this in case. everyone see the screen? Vaughn, can you see the screen here?
Yep, I can see it. Maybe
Okay.
we'll do Nafe as when we get on the pathfinding. I'll take over and do that part. Okay.
Okay, sure.
So if you can, yeah.
Okay, cool. So this is just a rough summary of what we've seen with the simple parallel problem here. At a very small amount of vector length, we've seen that the serial is actually quite faster than the parallel, right? And this is a test that I haven't shown, but in between, we can, as we throw more compute at the problem, we do see the parallel catching up a bit, but it's still not faster than serial. And at some point, we actually do start to amortize the parallelism overhead, but still we can throw more work at the parallelization. And at some point, with enough work, we do see our speed up getting to a reasonable amount here. And again, we'll never see perfect speed up because there is always a bit of overhead that we have to amortize. So at this point, I'm going to pass it over to Professor Betts, who's going to go through pathfinding.
Okay, thanks, Dave. Okay, so a little more about fast pathfinding, because this will help you with milestone 4. So we already talked about, we've got different algorithms that we can use. And some of the algorithms we can use are we can use A* in a doubly nested loop. And I've actually gone off and measured this for a problem with actually 24 intersections involved. So 12 pickups, 12 drop-offs. And iterative A* took 32 seconds. So 32 seconds is quite a while. And it means that that's going to chew up a lot of your time. So this isn't that big a problem. With your 45-second time limit, you wouldn't be able to do this for a big problem. Okay, changing the algorithm to a multi-target Dijkstra, we get rid of one of those loops, reduce the complexity, and it's a lot faster, 5.86 seconds for this problem size. If I make that, if I take the inferior algorithm running A* in a doubly nested loop, and I make it parallel, using the parallel 4 construct of OpenMP, we get about a 3.5x speed up and time drops to 9 seconds. So that's good. If we take our multi-target Dijkstra, so the better algorithm, make it parallel, the gains stack. The algorithm is faster, so it was 5.5x faster than using A* in a doubly nested loop. And parallelizing it makes it not quite 4 times faster, it makes it about 3.5 times faster still. So together that's 17.5 times faster. So what does this tell us? We actually got bigger gains, 5.5x, by changing the algorithm than we did by going parallel, which got us about 3.5x. But you can use both approaches. So usually you want to improve your algorithm first. Once you've got a very good algorithm, you can work on parallelization. And you can see from the start where we used not the best algorithm and it was serial to the end where we've got a parallel version of multi-target Dijkstra, it's a lot faster. It's gone from 32 seconds down to 1.84. Okay, so let me do a quick demo of what this means. Okay, I'm going to stop sharing this. And
I can stop the share, or should I stop?
I think I can.
Okay.
Let me see if actually, you might have to stop the share. Why don't you stop the share for a minute? Okay, so let me try sharing a different screen now. And let's see where I put I had a VNC session somewhere here. Let's see where it went. Oh, there it is. Okay. All right, so I'm going to share a VNC session so you can see this. And I'm going to use Nafe to tell me if he can in fact see this on my screen or on his screen. And let's see. Okay, Nafe, can you see my screen now?
Yep, totally.
All right, and I can't see the chat, so if you can watch the chat and see if there are questions, that would be great. Okay, this is a part of our...
we do have a question here.
Sure.
So we have, out of curiosity, is it going to be useful when we are loading maps?
It could make your load map faster. You can do parallelization there. For milestone 4, we haven't made the load map timeouts any tougher. So if your map loading time is fine, you could make it smaller, but you don't need to. It's not going to help you really with milestone 4. I would focus on making your actual traveling courier problem faster. So making load map faster is possible, but you're mostly at this point doing it because you feel it would be cool, rather than it's going to impress, will gain you many grades. Does that answer your question?
He says thank you.
Okay, so you're not going to understand all this code because you're inside the middle of a pretty big reference solution, but you don't really need to. This is a piece of code that does essentially what we just showed you earlier. We want to run multi-target Dijkstra, that's what this algorithm is, to find from one interesting intersection, one pickup or drop off, the path to all the other ones. And we need to do that in a loop. Okay, so every single interesting intersection becomes a source. And then for each one of those sources, we want to run a multi-target Dijkstra. And you can see here, I've commented out, this could be done in parallel, but I've commented that out. So I'm not doing it in parallel right now. I am running the unit test release build, and I'm going to run it on a test case that has about 24 interesting intersections. So k equals 24, there are 12 pickups and 12 drop-offs. So I'm just going to run it. I'm going to see what happens. Okay, so we're going to run it. You see some output coming out. The only thing I care about is how long does it take to compute this matrix of delays between my interesting intersections, because that's what this code I'm showing you is. Okay, so it says pathfinding took I'm going to stop this. Pathfinding took 5.85 seconds. All right, and so that's not terrible, but it chewed up a reasonable amount of our 45 seconds, and this isn't the biggest problem. This is only about 12 pickups, 12 drop-offs, so we're going to get bigger ones. So I'm a little worried if it's going to be fast enough. So what I'm going to do is I'm just going to make it parallel. Okay, so, and it was, given that we've written the code correctly, it was that easy. I'm just saying take this for loop and split it across multiple threads. So as Naif said, it's going to look at how many times we go through this loop, and it's going to split the iterations into 4 pieces, send them to 4 separate threads, should be faster. Okay, so I'm going to rebuild. Still in unit test release. Whenever I'm doing any time tests, I should always be using a release build, so that's what I'm using. And I'm about to run this as soon as it finishes building. Okay, so I'm running it, and hopefully the pathfinding is faster because we're using all 4 cores instead of just 1. All right, and it was faster. So I'm going to stop that again because it's got everything I needed. It took 2.27 seconds. So it's not quite 4 times faster, but it is nearly 3 times faster. And my speed up will probably get a bit better for big problems. So this was definitely worthwhile. But now let's go take a look at this. This looks really easy. I just put this parallel 4 around this loop and it was all good. You know, is parallel programming really that easy? And the answer is no. Okay, so I am going to, I'll show you what this does. But basically, I'm going to do some bad programming, okay? So then I've already prepared my bad programming. I'm now just enabling it. Okay, so I've just turned on this code, which is called bad parallel global 2. Okay, what is it? It's a global variable for a priority queue. You don't really care about the details of it, but you know we use a priority queue in Dijkstra, so this is our priority queue. So let's go see where that code is. So bad parallel global. Whoops, that's probably enough. So let's go look for that. Okay, so again, you don't need to understand all this code, and you won't, but this is actually the routine that does that multi-destination Dijkstra. Okay, so I'm in my multi-destination Dijkstra algorithm, and I need a priority queue. Here is a local variable that is a priority queue, and notice that it's shown in gray. The reason it's shown in gray is this, I've defined bad parallel global. So basically this line will not be compiled now. It's taken out, and instead my priority queue has been made a global variable. Okay, if you go look down through here, you'll see there's all sorts of code using the priority queue. Doesn't really matter. The key thing is I've just taken what was a local variable inside this routine and I have made it a global variable. And that is the way that many of you will have coded your milestone 3 solution. All right, so let's do a I'm going to change this now to unit test debug. Actually, I'll leave it release. Okay, we'll leave it release, and I'm just going to compile this. I'm going to get some warnings because what I just did, I didn't do it in a very clean way, but that's okay. The warnings just say, you know, you didn't do a very nice job using sort of the same variable name in different places, but I know it all does what I need. Okay, so now I'm going to run it. And let's see what happens. Okay, so it used to take us 2 seconds for the pathfinding with parallel pathfinding on. Map is loaded. We should now be into the pathfinding, computing that delay matrix. Used to take 2 seconds. Seems like it's already been longer than 2 seconds. Still going. What's happening? I feel worried. Okay, so this is actually not good. This should be done by now. And if I leave this running for another 2 minutes, 3 minutes, 5 minutes, this actually is hung. It does not come back. All right, and the only thing I did is I changed a local variable to a global variable. Okay, so it failed. Let's go back to where I called it. Okay, so again, this is my call of that multi-destination Dijkstra, and I'm doing it in parallel. Let's turn off parallelism. Let's see what happens. Okay, so I'm going to compile my unit test release again, and I'm going to run it again. We're going to see if this fixes it. Okay, so it's building. And now I'm going to run it. Okay, so I turn off parallelism. So I think my pathfinding should be slower. Okay, but I've loaded my map. Now the pathfinding is happening. Let's see what happens. Hopefully it finishes in a few seconds. And it's done. And it took 6.5 seconds. There's some bounce in CPU time numbers. So it used to, the last time I measured it, it took 5.9 seconds when I did it serially. It took 2.2 seconds when it was parallel. Okay, so it's slower, 6.5 seconds, because of the fact that I'm doing serially again, but it actually works. So it works with a global variable. So does anybody on the line want to just unmute or on the chat say, you know, what just happened? Like what would explain what we just saw? I'm trying to find where the various Zoom things are so I can find the chat. Let's see.
And I guess just to chime in, one small thing is if you see unexpected behavior in your parallel code, one way to actually ensure your sanity is to remove the parallelism and see if it works.
Yeah, so that is an excellent point. That is like the first debugging technique of parallelism, is turn parallelism off and see if the problem goes away. Dave, do you see anything in the chat? Because I'm actually trying to find my chat window.
A question from David Song again is he's asking, so is it not good to use multi-threading for global variables?
Global variables are dangerous for multi-threading. So remember, when you have a local variable, and it's not it's a local variable that's basically inside the function or the functions that it calls that are in the for loop that you made parallel. Okay, so all the variables that are local, that are basically declared in this function or its children, every thread gets its own copy. So that means they can't conflict with each other. Global variables, and also even any local variables that were created out here and passed in, you only get one copy. So that gives you the potential for the threads to essentially write all over each other's data and cause chaos. And that's what's happening. I have one priority queue when I made this global that all 4 of these threads are sharing. So I'm just going to basically, while we're talking, I'm going to start building this in debug mode, because we're going to basically see, we'll try to look at what happened. Okay. So yeah, global variables are very dangerous for parallel programming. If you have a global variable that you only read, that's okay. So for example, the connectivity between intersections, you're not changing. So you could have a graph that represents which intersections can connect to other intersections. And that could be a global variable. And that's actually okay, because all the threads are reading it. None of them are changing it. This priority queue, every thread is going to be doing a different multi-destination Dijkstra search, starting from a different intersection. They're all using the same priority queue to try to keep track of what to do next. So they're all reading and writing it, taking things in and out, and they're all doing completely different things from completely different start locations. So it is madness. It's chaos. It's like we just stapled, or not stapled, we tied 4 students together, gave them one exam answer book and 4 different exams, and they're all writing not on different pages, but they're all just writing at the same time in the exam book all over it. And then when you hand that in, they're all going to get 0, right? Because people are going to look at this and go, I mean, there's like a chemical formula in the middle of a calculus equation and something about political studies, and I have no idea what you're doing, and it's interleaved line by line. So it's chaos. Okay, so I just put this in unit test debug mode, and I've got parallelism on, and I've got my global variable being used for the priority queue. So I've got my bad parallelism. I've been running this, now I'm gonna debug it. So I switch to unit test debug, and let's see what happens. So it'll run a little more slowly because it's in debug mode instead of release. But hopefully I can get some more information. Okay, and now basically the program has crashed, and I can say discard and pause and try to see what happened. And under the debugging window, you'll see, whoops, okay, so it's pretty confused right now. Under window, you can look under debugging, and you'll see that there is threads. Okay, so there's a threads window, which you've never used before. Okay, but I've turned it on. I can go look at my threads, and I can actually see there are 4 threads. So this is part of why debugging is more tricky. I actually have 4 things going on. I can go look at those. So this thread, I just clicked on it. I can click on its call stack, and I can see it was in find all paths multithreaded. Okay, so it's here. And it basically has gone into some routines where it's in assembly line code. It's not even quite sure what's going on. So that looks a little chaotic. I can look at the call stack here, and let's see, where were we? Basically, I can see I started from this path search algorithm. So I was in that, and I was trying to push something in the priority queue. Okay, and then I'm deep in the priority queue there. So this thread is trying to push something into the priority queue. I look at the third thread, let's see where it is. Okay, the third thread, I just switched to it. I click on its call stack. I mean, basically the last few routines are not that interesting. They're basically abort in the middle of some kind of freeing of memory. So it's basically figured out that something's horribly wrong and called abort. But if I go back before that, I see I'm again in my pathfinding routine, and I'm in the priority queue. The pathfinding routine is trying to push something into the priority queue. So 2 of my threads were trying to push into the priority queue. Let's look at the third one. Look at the call stack. Again, the last stuff is not very interesting. That's where it got horribly confused and started throwing exceptions. But before that, where am I? I'm not in the priority queue. So this one's doing something else. Okay, so 2 of my 4 threads were in the priority queue trying to push things into it. The other ones weren't. That might give me some idea that the priority queue could be a problem. And if I run this a few different times, I'll probably get different errors. So let me stop debugging, and I'm going to try running this again. Let's see.
And that's the other thing about multi-threaded programming is there's also a bit of non-determinism when you're looking at the behavior of your program, especially if it's not working.
Yeah, particularly when it's not working. So these threads are all racing each other. So they can actually get different answers different times when the program in particular is not working. So if I run it again, it might actually do something a bit different. It's not going to work, but it will likely crash in a somewhat different way. So I'm debugging this again, and we'll see what happens. But from that previous one, I saw 2 things were in the priority queue trying to push data in at the same time. I've only given it 1 priority queue. So that's probably the source of the chaos. Is that they're both trying to update the priority queue. Okay, this one has actually been going for a while, so this now may be hung. And I just ran the debugger again, and you can see with no code changes, no rebuild, it looks like it's doing something different. And that's relating to what Naif just said. Multi-threaded debugging is often non-deterministic because the threads are racing, they're updating memory over top of each other. That's why we have a bug. They do different things each time. Okay, so I think this is hung. I'm going to pause. So I pause. I can go look at my threads to see where are they. So if I look at this first thread, let's see where it is. I look at its call stack. It's trying to take something off the heap. So it's in pop heap. So my priority queue, I'm basically trying to do a pop. Let's look at the second thread. So I click on threads, I click on that thread to switch, I look at its call stack. It's also trying to do a pop, okay? Trying to take something out of the priority queue. Look at the third one, look at its call stack. Okay, it's also trying to do a pop. Okay, so this is like, I'm getting more and more worried about my priority queue. I see weird things happening. Here I'm hung, and this one's not at the pop, but it was trying to get what was on the top of the priority queue. What's probably happening here is because they're all trying to update the priority queue at the same time, and they've three things are partway through doing a pop, trying to take something off the priority queue, and they've actually gotten the internal variables of the priority queue into a state that makes no sense, and they've caused an infinite loop. So you can see how difficult it can be to debug. And I think that's all. That's basically the chaos that can ensue from I had one global variable that multiple threads were reading and writing, and this worked fine when I made that local. So good practice when writing parallel programs is try not to have shared global state. Much harder to think about, much easier to have bugs with. And Nate, let's see if you can share the slides again. Let's go back to them and just wrap up.
Yeah. Vaughn, can you stop sharing your screen?
Sure, I think I can. Let's see. There, I've stopped sharing it. All right, so we were down a little further on. Yeah. So you click on 19. Thanks, Dave. Okay, so
let me just enable remote. 1 second here.
Thanks.
There you go.
Okay, so this is just a high-level pseudocode of basically what was going wrong there. And basically on the right is the code that worked fine, where we have a local priority queue. And on the left is the code that does not work if we try to make it parallel, because we have a global priority queue that's shared across all the threads. So watch out for that. Okay, so debugging parallel programs. This is exactly what Dave said. If something goes wrong in a parallel program, the first thing you should do is turn off the parallelism. So get rid of those parallel for pragmas. If the problem disappears, then you can say, oh, it's a parallel problem. It's probably a race condition. A race condition means you've got multiple threads writing to a shared variable, or at least one is writing and some other ones are reading. So their updates are getting confused. Once you suspect a race condition, you can run it in the debugger. You can use what I just showed you, the window debugging threads view. Lets you see the threads, lets you click on them so you can go check out what's happening with different threads. You can look at the call stack for each one. If you see that they're all accessing a shared variable at the crash point, which is what I was just showing you, then it's like that shared variable is likely your problem. But this can be a tricky thing to figure out. But I showed you I had to run a couple times, and then I became reasonably convinced it's the priority queue, because all the threads are they're crashing or they're getting hung, and they tend to be in the priority queue. Fixing race conditions, easiest thing, best thing to do is to privatize the variables. That means don't use global variables, use local variables that are essentially in the routines that were called by your parallel for, and then every thread has its own copy. You're not gonna have any race conditions, you're not gonna have any of this data corruption. Not as good, but can be done in certain cases, is to use OMP critical, which, because this will usually cost performance and it's a bit more complicated, that basically means one thread at a time will get access to that block of code. For something like output, writing to C out, this is a pretty reasonable solution. We would not want to do this with the priority queue, because the priority queue, we fundamentally need 4 different priority queues. It's not just a problem of we have 2 things updating at the same time. We have a problem with those 4 threads, each need their own priority queue. They cannot share one because they're all trying to put totally different stuff in it. Limits to parallelism. So Nave showed you one. If you don't have enough work, it doesn't work very well. Another limit is Amdahl's law. So you have a certain part of your work that is parallelizable, call that F. That's the fraction that's parallelizable. And you have n cores. This formula gives you what the maximum speed up you could get is. So if most of your code is parallel. That's what this green line is. 95% of your code can be made parallel. Then you get a speed up of up to 20x if you had a lot of processors. If only half of your code can be parallel and the other half is serial, then no matter how many processors you throw at this, you'll never get more than 2x speed up. So if you want to get really big speed ups, and you want to use a lot of processors, then you need to make sure there's very, very little serial code because it's going to limit your speed up. Okay, so parallel programming takeaways: improve your algorithm first. It's usually a bigger reward and it's usually easier to code. OpenMP is a pretty succinct and easy way to express parallelism. So those parallel 4 pragmas that we showed aren't very hard to write, so that's a good way to introduce parallelism. Modifying shared state's really dangerous. So try to avoid modifying shared state. It minimizes the bugs. Actually also can improve performance. So privatize variables. Make them local variables so every thread gets a copy. Parallelize large chunks of work. There is an overhead to start threads, so don't try to make little bits of work parallel. As Naif showed, that's not going to help. And parallel programming is fundamentally hard. So even experts get it wrong. There are open research questions about how do you parallelize various things, what are good algorithms to parallelize, and parallel debugging is fundamentally much harder than serial debugging. So you don't want to do it on the most tricky parts of your program, and you don't want to do it as your first attempt to speed something up.
Oh, sorry, I may have clicked on the screen. Yeah, there you go.
Okay, so in M4 suggestions, as always, agile development, get something simple working first. So you can use a simple travel time heuristic. You don't even need to get the right travel times from a pathfinder. You can use geometric distance, as Naif said. You can use a simple ordering heuristic, so maybe a greedy algorithm, and return a legal solution. Then start doing various improvements. And you can split this across different team members. So you can have somebody trying to get better cost estimates using the techniques we just talked about, pre-computing exact path delays. You can have another person working on perturbation operators to get better orders. Parallelization is not the first thing you should try. It should probably be, it's one of the harder things to do. And while it can yield reasonable gains, it's not as important as getting good algorithms. So don't do it first. It should be one of the last things you try if you have lots of time. And that is it. Does anybody have any questions or any questions on the chat?
Let's see.
So Naif, if you stop sharing.
Oh, sure. I can stop sharing.
And then I can see if there's anything going on in any other windows. Thanks. Okay. So if there are no other questions, then we're done.
Yeah. If any of you realize you have questions, you can also pop in for tomorrow's tutorial or at least near the end and ask us questions then. Also Piazza is a thing. So.
Okay. All right. Thanks, everybody. We'll post the recording of this as well.